Regions between curves, Part 2, integrating with respect to the y-axis. In Part 1, we integrated with respect to the x-axis. And we said that to find the area, what we're doing is we're adding up infinitesimally thin rectangles, each of length f minus g and width dx, and adding up rectangles from x equals a to x equals b. Now here in Part 2, we're going to reverse the roles of x and y. We're going to have x written as a function of y. So given a y value, what is x? In the graphs below, we want to find the area of the regions between x equals f of y and x equals g of y, where y runs between c and d. The process to find the area of the region plays out in a similar manner as when we had y as a function of x. Here are some things to keep in mind. The independent variable y runs between c and d. The more positive function x equals f of y is to the right of the more negative function x equals g of y. The width of each rectangle is dy, and the length of each rectangle is f minus g, so f of y minus g of y, the right-hand curve minus the left-hand curve. Let's do an example. Find the area of the region bounded by the graphs of f and g and the x-axis. One way to integrate this is to break the region into two sections and integrate with respect to the x-axis. So I would have one integration from -6 to 0 and another integration from 0 to x. From 0 to 2. So I could do it that way. Not a big deal. But another way I could do it is I could integrate with respect to the y-axis, and then I would just have one integral to do because there's no differences. It's always right-hand side minus left-hand side. So to integrate with respect to the y-axis, we need to rewrite f and g so that x is written as a function of y. So we've got y equals x of 3, x to the third power, and y equals x plus 6. So that's how the functions were given to us. We need to change them so that x is a function of y, and to do that, solve for x. So if y equals x to the third, then x equals y to the 1/3. And if y equals x plus 6, then x equals y minus 6. So the curve on the right is x equals y to the 1/3. The curve on the left is x equals y minus 6. The length of each rectangle is the curve on the right minus the curve on the left. The width of each rectangle is dy. And we're adding up rectangles from y equals 0 to y equals 8. So this is what our integral looks like. The only thing we have left to do is to go ahead and integrate and evaluate. So find the antiderivative. Before finding the antiderivative, you can simplify the integrand. Then find the antiderivative and evaluate. When you evaluate, you get 28 square units. Let's do a different example. Find the area of the region in the first quadrant bounded by the graphs of f and g. So again, I have the curves written in terms of x, and if I want to integrate with respect to y, I'm going to have to rewrite my curves. So as the curves are given to me, this is my graph. We need to find the point of intersection. You can either use guess and check, or you can solve this algebraically. Guess and check works pretty nicely. It looks like x equals 8 will work. So check x equals 8, and indeed it does. Now the next thing I need to do is I need to write x as a function of y. After I do that, I need to find the length and width of each rectangle. So the length of each rectangle is the right-hand curve minus the left-hand curve, and the width is dy. Now, what are your bounds? You're integrating from y equals 0 to y equals 4. After you do that footwork, you just need to find the antiderivative and evaluate. So find the antiderivative and evaluate, and when the dust settles, you get 56 over 5. Now, we could have done this by integrating with respect to x and using two integrals. We could have also what we did, and we could also do what we did, and that is to integrate with respect to y and rewriting the functions so that x is a function of y. That's actually what we did. However, I do want to point out that you are allowed to think in this class, and please do not hesitate to do so when that makes your life easier. Now, an example of how thinking can make this problem easier. What we could do is we could notice that the region R is the region R1 minus a triangle. So the area of region R is the area of region 1 minus the area of region 2. Now, the area of region 1, I can integrate, I can find that pretty easily by integrating with respect to the x-axis. So R1, I would just integrate my upper function, x to the 2/3, from 0 to 8. And then region 2, that's just a triangle. So I just go 1/2 height times base. And so if I go region 1 minus region 2, I'd get the same answer, 56 divided by 5. And that's a perfectly legitimate way of doing it using calculus and doing it by hand. So you may want to think in terms of looking for shortcuts like that. On the other hand, if you are asked to integrate with respect to the y-axis, you now know how to do that. So take care and have a great day.